Hello and welcome to Tuesday's edition of Cracking the Cryptic, and an exciting day for me because it's Fistamofel's new puzzle that I'm going to have a go at. It's amusingly titled Moles, this one, which I suppose only adds further to the menagerie of animals that seem to live in Sudoku world, what with its glum hippos, its normal cats, its prowling tigers, and now moles as well. Now, before I get on to the rules of this one, I'm delighted to say that following yesterday's video, which of course featured Demono's latest puzzle, Demono is going to be producing a constructor video about that puzzle and how he made it, which will be wonderful. Oh, by the way, thank you to those of you who've written nice things about the little tune I played in the outro to that video yesterday. You're very kind. But I'm hoping that Demono's video will be part of a series of videos from constructors. I've had quite a few contacts now from a variety of people who are very keen to add to a sort of video series we can make in that regard. So if you're an aspiring constructor, watch this space. I think there's going to be quite a lot of interesting videos on the channel in the next few weeks. Other things to mention, Marge. Marge is, of course, the poor lady who inherited from her grandfather not a huge fortune, well, a different sort of fortune. This Sudoku is what he left her in his will. Now, many of you have managed to solve this puzzle and have found the video that it leads to. It leads to a video from the late grandfather himself, in which he explains what Marge needs to do next. Now, if you've not done this, do it soon, because I think Marge is closing in on finding this inheritance. You just need to solve the puzzle, have a think about what these cages might mean, and if you're still stuck, don't ignore this beautiful pattern around the edge. Can you see any letters hidden there? There might be some. Anyway, that's a little hint. Yeah, so where's this all leading regarding Marge's inheritance tax? Not inheritance tax. That's a very boring subject. Inheritance. We shall see. And it's, yeah, the announcement is imminent. We're also, of course, 1st of May, which is coming up very soon. We have an amazing treat for you if you're a patron of the channel. Matthias Martinka has constructed what I consider to be one of the great puzzle stroke Sudoku hunts certainly I've ever solved. It's absolutely exceptional, and that's what we're going to release for you guys on the 1st of May. So, exciting times. Now, with all that said, let me read you the rules of Fistamofel's new puzzle. We have got normal Sudoku rules apply. Digits may not repeat within a cage. In cages, digits must sum to the small clue in the top left corner of the cage, if given. So there must be, okay, yeah, we've got or cages that don't have totals in the top left corner. Okay. And along thermometers, digits must increase from the bulb end. So there are some thermometers in this one. So what that means is, imagine this square was a 2. This square would have to be higher than a 2. It doesn't have to be 3. It could be 5, for example. It just needs to be greater than 2. And then as we move up the thermometer, the mercury rises, and this square would have to be higher than 5 and could be 8. So 258 would be absolutely fine as a way of filling that thermometer. Do have a go. The way to play, as usual, is to click the link under the video. Now I get to play. I've been looking forward to this. Let's get cracking. So, how shall we do this? We shall. How big are these ones that don't have one? Okay, so that's a 9-cell cage. So that's immediately, by the way, making me think about this square and where it can go in box 4 of the grid. It's going to have to go in one of those 3 squares because it can't repeat in its own cage. And therefore it's going to be in one of those 2 squares at the bottom of the grid. And that is absolutely useless by the looks of things, so perhaps that's not where we start. This cage, which doesn't have a total either, 1, 2, 3, 4, 5, 6, 7. Okay, that's 2, 3, 4, 5, 6, 7. So because of the secret, now if you don't know the secret, where have you been? The secret, of course, is that if you consider what any correct row, column, or box of a Sudoku adds up to, it will contain all of the digits from 1 to 9. So it will add up. If you add up those digits, you get 45. So let's have a think about this cage down here. It's a 36 cage and it's 7 cells large. Now, that means we know if it was 9 cells large, it would add up to 45. So the two cells or the two digits missing from this cage must add up to 9, because they must add up to 45 minus 36, which doesn't really ring any bells with me. We've got a 3, 4, 5, 6. We've got another 9-cell cage here. So there are two unmarked 9-cell cages, although we don't really need the totals because we know the total for a 9-cell cage would have to be 45 because all the digits in the cage are different. Now, right, okay, well this one is a little bit more interesting in that I'm interested in those 3 squares, because these 3 squares have to be the same as those 3 squares. And how do we know that? Well, we know the 9-cell cage contains all of the digits from 1 to 9, but we also know that box 9 contains all of the digits from 1 to 9. So, where are we going to put this cell, for example, in this 9-cell cage, which must contain this square? Well, it's going to have to go, it can't repeat in the box, so it's going to have to be in one of those 3 positions. So, those 3 and those 3 are the same. Let me just colour those in. Now this is, so this is, right, okay. Okay, well now we can do some work in box 6, because let's have a look at this domino of purples here and ask where this domino of purples goes in box 6. Well, whatever's in those 2 squares cannot repeat in the 32 cage, so it's not in any of those 5 cells. By Sudoku, it's not in those 2 squares, which means that this domino here is exactly the same as those purple squares. So I'm going a bit crazy with my colouring here. These dominoes are the same digits. Let's start there. And we know that these 2 digits have to appear in these 3 digits. And that one's on a thermometer. Oh, right, okay, so this digit is the same as that digit. Because one thing we can say with certainty is that this cell, because it's on a thermometer with these 2 squares, it can't be the same digit because digits have to increase along the thermometer. So if this was a 1, you can't make either of these 1s. If that was a 5, you can't make either of these 5. We have to increase. So this square, which we know is one of these 2 squares and therefore has to repeat in these 3 squares, has to be the same as that square, which means it's not this square. This is lovely. Okay. Yes, okay, so now let's uncolour this square, because now what we've discovered is that this square, and this square are the same, which means the other thing we can say with certainty is that those 2 squares are the same. Use orange today. Now, what does that mean? So now we know orange is in one of those 2 cells, because we know, again, orange must appear in one of those 3 and it's not the same as purple. So we know, let's make that one green, we know there must be a green and an orange in box 5. So now I'm wondering where green goes in box 8, look, because I can see, I mean, green can't go there because of Sudoku, it can't go on its own thermometer, and it can't go in a column that already contains a green in one of those 2 squares. So green is in one of 3 places. Probably not that helpful. Green in this box can't repeat in its cage. Green would have to be in one of 4 positions in box 7. That's probably going a bit far. Right, hang on a minute. Let's have a think. We have got so this all feels like it's very deliberate, doesn't it? And clever. So purple has to be in one of those 4 squares by Sudoku and one of these 3 squares by Sudoku. And purple is not 1 because it's in a 2nd position along a thermometer. So this square is not 1. This is not helpful. Okay, I think we're going to have to do something else here. Let me just try and spot something. I'm really not sure. We've got a 25 cage there, in 5 cells, so that's not ringing any bells with me. 7-cell cage. Oh, for goodness sake. Right, okay. This square, row 3, column 2, where does that go in box 7? Well, let's think about this. Because of this cage, and the fact we can't repeat digits in a cage, whatever is in here cannot be in those 3 squares. It can't be in these 3 squares by Sudoku, so this square must have a mirror in one of these 3 squares in box 4, which means that blue, or this outlined blue shape, is in one of those 3 squares in box 7. Well, it can't repeat in its own cage, so whatever goes here can't be in this domino. So that square and that square are in fact the same digit, and that might matter. Let me just think about this now. Do we know anything? We know green is not the same as... Sorry, we know blue is not the same as green. We don't know whether blue is the same as purple or orange. Okay, so that doesn't look good, does it? Let's try and find... I think some of these cages, like this one, there must be some... This square is probably weak. Yeah, again, this square, where does it go in box 3 of the grid? Because it can't repeat in its cage, whatever goes in there can't go in there by Sudoku, can't go in there because it would repeat in its cage, so it goes there. So those 2 digits are the same. I'm now allowed to use yellow as a highlighting colour because of the new blue outline selector, which many of you have commented you really prefer. So thanks to Sven, our programmer, for creating that. Now, yellow's in one of these. So, sorry about this. 1 second. Let me try and spot something. I keep coming back. This square feels weak to me. I don't know why. This square goes into one of those, goes into one of these. I think that's a red herring. I suppose this was a 9-cell region, wasn't it? So those 3 squares are the same as those 3 squares, which I can't see what to do with that. Oh dear, this is not going very well now. The 32 cage is missing 2 cells. It's a 7-cell cage. It's missing 2 cells that sum to 13, because obviously 45 minus 32 is 13. Right, okay, so this domino here adds up to 13. How do we know this? Well, we know this because whatever we put in this square or this square cannot go in the 32 cage, just because of the geometry of the cage. If whatever goes here obviously sees those squares in the box and these squares in the column, and the same is true of this square. So these 2 squares are the missing digits from the 32 cage. That's interesting. It's almost like there's a hidden 45 cage there. I wonder if there are more opportunities to do things like that. I've got to remember, do I want to highlight this? I'm not sure I'm going to highlight that because, or maybe I will. I'll highlight it in light grey just to try and remind me that there's something funny about those 2 squares. Now, are there any other... This one is a 7-cell cage. Yeah, I can't see a cell that sees all 7 of those cells. No, I can't see any cell that sees all 7. So I don't think there's an opportunity to turn this into a virtual 45 cage. How about that one? That one, yeah, those 2 squares see all 7 of those. But we don't know what the total is for this one, so that's probably not important. What about that one? 36. Yeah, okay. What about those 2 squares? Those 2 squares see the entirety of the 36 cage. So these 2 squares have to add up to 9, i.e. 45 minus 36. Now, those two squares sum up to 9. I don't know what that means. There's something here we're missing that's very fundamental, and it is going to be embarrassing if I don't spot it soon. That square, yeah, hang on. Oh, goodness me. This square can't be in any, it can't repeat in its cage, can't repeat in its column. So where does this square go in box 5? Well, it's got to be in one of these 3 squares, but we can do better. This is important, I think, because this square cannot be orange, it sees orange in its row, and can't be green because it sees green on its thermometer. So that square and that square are the same digit, which we will make black. Which means black is in one of those, which looks completely useless. And we've got an interesting, actually that is interesting, isn't it? We've got 5 different colours now in column 6. So is there some way, maybe we're meant to try and colour the whole of this column somehow. Oh, right, now, hang on, these squares are interesting now. I should have seen these straight away. I was too focused on the numbers, I think. These 2 squares, where do they go in box 8, look? Well, they can't go in the same cage, and they can't go in the same row. So these 2 squares, which are higher than blue... Oh, no. Hang on, these squares see purple. So these 2 squares are the same as those 2 squares. So one of these squares is black. Now... Oh, no, better than that. One of these squares is black, but these 2 squares see green in their box, in their cage, look. So they're not green. Whatever you put here cannot be the same digit as goes in this square, which is green. So these 2 squares are... They're not purple. They are black. One of them is black. And one of them must be this digit, therefore, which cannot be green. So we'll use dark grey. That square can be dark grey. So now, yeah, now we've got a black, dark grey pair in row 9. Now I'm suddenly wondering about the thermometers. Lots of these colours are on thermometers. Hang on a sec. Let me think about this. So... hang on a minute. Black is higher than green. Green is higher than purple. So this cannot be black. If this square was black, black would have to be simultaneously, black would be lower than green, and black would be higher than green. I don't know if that's clear, but it is true, because we know the very simple way of thinking about this is to look at this thermometer. In fact, it might be to even put some digits in here. If we look at this thermometer, you can see green. The minimum green could be, according to this thermometer, is a 2. Let's make green a 2, just to show you what I'm thinking here. So that means the minimum black can be is 4, because we'd have to go 2, 3, 4. Now, what would happen if we try and make this square black? Well, that would be a 4, that could be a 5, that could be a 6. That would all be possible, which would mean this would be a 5. And now we need one of these two squares, which is green, to be 2. Well, it can't be. It's got to be higher than 5. So this does not work at all. And that means that we know this square is not black. So that is definitely grey. This is definitely black. And we have... well, what do we have there? Do we have anything, actually? We've got... does that mean... yeah, same thing. We can now apply back on this thermometer, can't we? Because we now know, because black is greater than green, and grey is less than green because of the way it interacts through these two thermometers, we know that on this thermometer, grey is less than black. So actually we are managing to colour some of this in. And in fact, if you look at the puzzle now, this is why this puzzle is called moles. This is why it's called moles. It's because things keep jumping round the grid. They sort of burrow here. This blue burrows here and pops up here. The grey burrows, I don't know whether it burrows here or something, but then it plops up here and here. It's almost like the thermometers are mole holes, I think. Now, what I'm interested in, I'm actually interested in this square, because this starts the run of moles. I mean, that looks like, if we make that 1, you can see blue has to be at least 2. Grey has to be at least 3. Black has to be 4. So, at least 4. Oh no, but black can't be 4 because... oh no, hang on. Let's leave black out. I can see that why I need to leave black out, because I need to think about what happens to grey when it hits this thermometer. So grey has to go at least 3. Grey is at least 3 at this point. So purple is at least 4. Orange is at least 5. So now purple is at least 4. So now we don't know what happens to... we don't know what the order is here. Look, we don't know whether orange comes before green or not, I don't think. So I don't know... okay. So I think all I can say about this square is this could be green and it could be a 5. So green is 5 at least, but I don't know whether it's higher than that. 6. So now... okay. So now black is at least 7. So that square's at least 7. That square's a 6 at least. That's a 4 at least. Black's a 7 at least. Yellow is an 8 at least. And look at that. We've actually... so now you can't... there's only 1 degree of freedom on the whole mole trap that we've created here. Because we can't make this square greater than 2. Because if we make this greater than 2, this square will be greater than 9. In fact, better than... oh, ooh, hang on a moment. Let us pay closer attention to column 6 all of a sudden. These digits I've put in here are the minimum value it's possible for each of these cells to be. Now, let's have a look at those 4. They have a minimum value in each case of 6. So these squares absolutely must be a 6, 7, 8, 9 quadruple. And that means that square's a 5. Because the minimum value of this square is 5, and it cannot be a 6, 7, 8 or 9, because the 6, 7, 8 and 9 have to go in those squares or the puzzle's broken. So that square, we don't know what colour it is, but we know it's a 5. And therefore we know that purple is 4. That's absolutely beautiful. I mean, Fistemafell, yet again, just mesmerises, because that is so gorgeous, the way that we were able to sort of get this run of digits up here, and the way the thermometers interact in order to force individual digits to be high enough that there is a restriction. So, yeah, this has to be 4 because we knew it had to be at least 4, and because of the rest of the column, it cannot be 5, 6, 7, 8, or 9. So now purple is 4. But grey is at least 3. Well, now it can't be 4, so it must be 3. So grey is 3. Grey is 3. So blue is 2. And this thermometer, which started it all off, is a 1. Now, can we go further? We now know. Just trying to see, is there a way I can use... I can't push this digit too high because that will push this up and not leave enough room for this one. So that certainly can't be an 8. So that's definitely a 6 or a 7. This one I think is free. That one's a 7 or an 8. That's an 8 or a 9. Oh dear. Oh, I was just thinking, if I knew this was a 5, look, I would know what that 13 adds up to. I would know it was a 6, 7. If this was a 5, that would have to be 6 and 7, because 4, 9 and 5, 8 wouldn't be available to make these squares add up to 13, which is what we know they must add up to. Well, there's something else down here that did that. There was a virtual... these two... yeah, here we go. These two squares have to add up to 9. So this square is a 7, which means black is not 7. Hang on, this is huge. Is that right? Let's just double check that. So we know that, yeah, whatever goes in those two squares cannot go in the 36 cage. So these are the missing digits from this virtual 45 cage. They must add up to 9. When we know this is a 2, that becomes a 7. And now black is not 7. So it must be 8. And we know it must be 8 because it can't be 9. Because if we put 9 in here, yellow would be 10. So this is... well, it's absolutely beautiful. So that gives us 8. Yellow is now definitely 9. So we still don't know what green is, though. But this domino now sees 8. And it adds up to 13. So this is not 5, 8 or 4, 9. That's 6, 7. Now, oh, look at this. Look at this. Let's think about what orange is all of a sudden. Now, orange, this square in orange sees 6, 7, 8, 9. So orange is not 6, 7, 8 or 9, but orange is at least 5 from the thermometer work we did earlier. So it is 5, which means that one is orange, which means that one must be green, which means green is at least 6. Oh, look, it is 6 then. Look at this. Green cannot be higher than 6, because if it is, what are you going to put in that square? You can't put 7.5 in this square, and it needs to be less than 8. So it must be 6, that must be 6, that must be 7. And that must be 5 using this logic. And we've suddenly, I think, filled in every thermometer. And that was absolutely gorgeous. Now, hang on, there's a 6 in one of those two squares using the green. So what do we do next? That's the next question. This square is a naked single. It's a 1 because column 6 has not got 1, 2 or 3 in it. There's a 2 and a 3 in the row. So this is a 2, 3 pair. Okay, that's good. But does it tell us anything? Oh, there's a 2 here, so this is a 2, 6 pair in the box. And now we need 5 and 9 into those squares, which means we know the value of this square. That's a 4, and it turns purple. Okay. Now, what does that mean? So purple is quite restricted in this 9-cell cage now. It's got to go in one of those 2 cells, because we know it must make an appearance in this cage somewhere. We don't know much about that one, do we? Yeah, this 7-cell cage here I think was just being used to give us that these 2 digits were the same. 25 cage. So, right, so these 4 squares add up to 17. 17 and 28, 36. These 2 squares add up to 9 in order to make sure the box adds to 45. 2 cells adding to 9 that can't be 5, 4, 3, 6 or 1, 8 have to be 2 and 7, which might be useful because I can see it resolves the 2 and the 6 down there. This square's a 3 by Sudoku now because of this 3 there, and those squares are 1, 4 and 9, which is lovely because that finishes the 9 and the 5 at the bottom. And now all of a sudden we are starting to suck diesel or cook with gas, whichever you prefer. 1, 4 and 5 in those squares. Nah. Oh yeah, this is nice. Where does 2 go in box 3? And the answer is I haven't got a clue, but I do know it's in this cage. So if it's in this cage in box 3 because of this 2, it's not there as well because that would repeat it. So those go into the grid. Okay, now what do we do? We've got 7s, look, in those positions. So 7 in this row has to be in one of those 2 positions. These squares are 1, 2, 7 and 9. I've got a 2, 7 pair. That's probably helpful. 2, 7, so this must be 9. This must be 1. 9 must go here by Sudoku. 9 is no longer in this cell. This is a 1, 3 pair. It's just using the power of the 1, 3 in the grid now. And those 2 squares are 2 and 8. And the 2 and the 8 resolve the 2 and the 7. And we can place 2 in that square. 5 is in one of those squares. 4, look, is in one of those 2. Now what do we need to have been missing from this 34 cage? It's a 7-cell cage, so it's missing 2 squares that sum to 11. And those squares are not 8, 3 or 2, 9. So there must be an 8 in this cage, which is definitely in one of those 2 squares therefore. So it's either missing 4, 7 or 5, 6. I'm not sure how to do that yet. Okay, so 3 in this box must be in one of those 2 positions. So 3 over here is in one of these 2 cells. 3 here gives us the 3 and the 1, which places a 4 here. That resolves the 1 and the 9 once we stare at it. Now 9, look, we don't know about yet in box 4. 3 we nearly know about, but not quite. Come on, where do we look for more clarity? Here's something a little bit interesting. 1 has already made an appearance in this 45 cage. So the 1 in box 7 can't be in those 2 squares, and it can't be here because of that 1. So this must be a 1. So 1 is in that domino at the top of column 3. Yeah, and here's a little bit of logic. We know that the cells missing, the digits missing from the 34 cage are 2 cells that sum to 11. So 1 is not missing from that cage. So 1 is in one of, in fact 1 is there. That's what we've learnt from that, which gets us this 1, which means this square is a 1, and that's all good. Come on, a little bit more, and we'll crack this one. Where's the next place we need to look? We could... I don't really see any way of doing this 6, 7 and 8 in short order. Oh, look, those 3 squares are probably where we look now. We've got 5, 7 and 8. Oh yeah, we can get the 3. Let's just get the 3 and do that. So 5, 7 and 8 into those squares. Now we know there must be an 8 in this cage. So that's definitely can't be an 8. So this is a 5 or a 7. And the other digit that's missing, this digit, has to be the counterpart to this one that adds up to the 11 that we need. So this is either 6, which it looks like it can be, or 4, which it looks like it can be. That's very annoying. Yeah, okay, don't see how to do that, sorry. So we're going to have to keep going. 1, 2, 3, 8 maybe? Yeah, hang on. This 8 means there's a 4-8 pair in the 45 cage there, so we can see if that does anything to this column. We need 5, 6 and 8. So that square's become a naked single, I think. No, not 5, 6 and 8, that's wrong. I've already got 8. 5, 6 and 9, that's not a naked single. This is a 6, 9 pair. Good grief, Simon, get a grip. This 6, 9 pair does resolve the 9 though. That's got to be a 9. So we now know exactly what those 4 digits are, because they have to be the digits we've not yet placed in this 45 cage. So they're 2, 3, 5 and 7. So the 3 can only go in this position. One of these 2 squares is a 2. I've now found a 5, 7 pair in row 3, so that's not 7 anymore. So we must need 4, 6 and 8. This is a 4, 6 or an 8 apparently. Okay, don't know how to do that. 5, 7. Oh, hang on. Right, where does this square go in box box 4 of the grid? We know it's not in any of those squares, so it must be in one of these 3, and therefore it must be in one of those 3. Now it therefore can't be 5, that must be a 7. Which actually is going to be lovely, isn't it? That seems like it might have cracked the puzzle, to be honest, because all of a sudden things are going into the grid with a little bit more alacrity. That square's a 7 now, that's a 6. This square is not a 6. Oh, it still doesn't resolve, but that square's now known. That's got to be a 5. And 5 makes an appearance up here. Those squares are 3, 4 and 8. So the 3 can only go at the top of the grid. And this is a 4 or an 8, which means nothing. It means nothing to me. And that square is a 6 or a 9, which is a 6. Okay, good. So 9 has to go here, 5 has to go here, 4 and 5 go in. Now, this is good. Now 5 has finally been pushed out of the 34 cage. So once 5 is out of it, we know that the other digit that's out of it must be 6. So we can fill those in. That resolves the 4 and the 8 over that side. The 8 and the 7 can go in. This can be a 6, 8, 7 combination. And that finishes the puzzle. Yes, and I know I haven't done all the colours. You'll have to forgive me. Look, what I can do today, I'll try and do it, is I will... There you go. I didn't do all the colours today. I've learnt what Control A does. Thank you so much for watching. Another brilliant puzzle from the great man. Just stunning. I have tried to persuade him to do a constructor video, and he did say he would try. But yeah, keep your fingers crossed. And maybe put in some good comments on this video, and we'll try and persuade him. Thanks so much for watching, and we'll back later with another edition of Cracking the Cryptic.